Okay, well, while we're getting set up with some AV, I think it's actually a perfect time to thank Marco and Peter and everyone who was involved in organizing this. It's a fantastic session. Thank you. And I appreciate the point about keeping on time and the construction process. I don't want to be marked in red here for falling behind schedule, so I'll try and keep us moving. What I'm going to show you right now is a new result. It's a, I hope we could show it, but it's a video of new results we have with surgical robotics. And it is perfect. We're in business. Thank you. So I'm just going to start off with this, and hopefully the sound will kick in as well. Let's try it.
We are investigating if a Da Vinci surgical robot can autonomously perform tedious subtasks. This video demonstrates new results involving cutting and deformable tissues using a learning by observation approach described in detail in the paper. The first subtask is linear debridement, removing a linear section of cancerous tissue. We use plastic putty as tissue phantom. A computer vision system identifies the linear section and guides the robot to extract it in subsections. In 5 trials, the robot successfully extracted all target tissue in pink. The next subtask is spherical debridement, removing a set of randomly placed spherical sections of cancerous tissue. We use plastic putty as a proxy for healthy tissue. Embedded in the healthy tissue are multiple targets made of a viscoelastic material shown in pink. These targets represent damaged or tumorous tissue. A computer vision system identifies the target spheres and guides the robot to extract them. In 50 trials, the robot achieved a 96% success rate. This subtask is from a laparoscopic surgeon's training kit, cutting a circular pattern from a sheet of gauze. A computer vision system identifies the circle and guides the robot to cut along the lower and upper halves. The second gripper stretches the gauze, while the first gripper cuts the pattern. In 20 trials, the robot achieved a 70% success rate with a 99.89% cutting accuracy in successful trials. The video is sped up by a factor of 8. The robot is currently half as fast as human experts. However, not all trials were successful. We show here failure modes of this subtask. We are working to improve robustness for future work.
Okay, so there's a paper that we just submitted to ICRA, and it's available on our website. What we're trying to do in this work is to address this idea that the Da Vinci has been out for at least a decade, and it's been being used all around the world very successfully, but there's almost no one has done anything autonomous with it for a variety of different reasons. So we've been looking into this problem. Peter and I have been studying it. A few years ago, we looked at the problem of suturing, autonomous suturing, which is extremely difficult. And an approach we tried, this is a few years ago, was to build on his results for helicopter with apprenticeship learning. By being able to perform very complex maneuvers with helicopters by observing human experts and learning from their trajectories. We applied something very similar, so we, in this case, observed human surgeons performing the suture operation. And the idea is essentially like this. We have, let's say, a figure 8, just to illustrate, in a plane, and then we get a number of observations. And then what we do is we treat each of those as observations of some underlying latent control signal. And then what we do is we time align them using dynamic time warping, and then we apply a linear model. We apply Kalman smoothing to try and infer the underlying model that's common to all the observations that we saw. So if you had these observations, you might infer a trajectory like this. This is a control signal that's applied to the arm. And then what we do is we execute that, and it's on the system, and then we do a series of steps of iterative learning after that. So we fine-tune the resulting motion to bring it closer to the desired trajectory. And after we do that for a few iterations and bring it close, relatively close, then we do something different. We increase the velocity. So the idea is to start speeding up the trajectories. So this is an example of what this can look like. This is a 1 time, that's the speed approximately of what the humans were doing. Here's 4 times, here's 7 times, here's 10 times. So what you're able to do is to get a trajectory that's pretty close to what we desire, and at higher velocities than any of the human demonstrations. So we call that, the term we've been using is that superhuman performance. We've done some work since then with the Raven, the open architecture surgical robot that was developed at the University of Washington. And last year we reported on some study of a task called debridement, which is to pull out fragments of dead or decaying tissue. And in this case, we used discrete pieces of foam sitting in on a table. And that led us to this year to start work with the Da Vinci. And many of you may be familiar. If you're not, the Da Vinci has, Intuitive has very generously started offering the first generation Da Vinci robots, the hardware, to research groups. And I believe there's 14 of these out there now. And what they don't supply is the controller. So you have to rebuild the controller and the software. But working with the team at Berkeley, we were able to do that. And that was our project over the last year to get to the point where we're able to consider these new subtasks. And so there's a variety of related work. People have been looking into this, and particularly modeling deformable tissue is extremely challenging, especially when you start to cut tissue and you change the topology of a mesh. So we looked at these particular 3 subtasks that are, this again is, the first 2 on the left, we're using this putty-like phantom that we made out of Elmer's glue. It's also known as GAC. If you watch, what is that TV channel? Nickelodeon. Turns out to be very helpful material. And then the far one on the right is actually one of the training tasks they use for surgeons. It's part of the research kit, the fundamentals of laparoscopic surgery. And we've been looking at an approach that we call, that was actually in a dissertation from 2004, learning by observation, where we basically observe the human, in this case, and we observe humans doing this through teleoperation, and we use that to try and infer a finite state machine. So partition the task into segments, and then be able to once we have the finite state machine, there's a number of parameters. We try and set those and do parameter tuning on those and then if necessary, we can adjust the finite state machine. We go through this iterative process to generate this finite state machine. And actually, it's very interesting, the idea of using the DP segmenting that Mike Jordan was talking about today may be relevant here. What we've been doing is somewhat of a very hands-on process right now, but we see it as hopefully something that we can generalize that will apply to other subtasks. The initial results here were exciting. I think there's certainly, this is a somewhat artificial environment. We have a nice clear definition of the 2 colors of the materials, but this is a trial where we had 5 trials of removing this little linear strip, and you can see that it was always successful. In one trial, in the 4th column here, or 4th row, we had to do a second retraction because the cut failed. So the system was able to identify that and then go back and do it a second time to remove that. For the spherical, the little small dots, we ran about 50 trials and had 1 failure. Again, it was a sensing failure, so it's the perception are big challenges here. And then in the pattern cutting with this fabric-like tissue, here we've had about 70% successes. This is where we perturb the position of the circle. But what I was surprised, we were surprised to find that the actual score, and this is a measure of the accuracy using a symmetric difference metric, was extremely high. So they're able to actually cut on par with what human surgeons are able to do. And right now the speed is only half as fast as a human expert. So I want to acknowledge the students, several of whom are here in the audience, in particular Ben Kehoe, Sid, Aditha, that's my timer telling me I'm out of time, Animesh, and Sylvia's in the room too. Sachin Patel is a postdoc who's working with us. And let's see, and this is also part of a larger project that we're funded under the National Science Foundation to do multilateral manipulation, both for surgery and for manufacturing applications. And the last thing I'll say is that we see this as part of a larger exploration, larger research agenda having to do with cloud robotics. Thank you.